Okay, here we're going to look at that same system we looked at initially. Okay, this one that we looked at back here. Okay, but we're going to add an open feed water heater to it. So we're going to pull off at 100 psi. So pressure 2, 5, and 6 are all at 100 psi. Now the states are exactly the same. State 1 is the same as it was before. Okay, 1600 psi, 1100 degrees Fahrenheit. Okay, 2 gets pulled off, but then 3 ends up at the same point that 2 was at 2 psi, or I'm sorry, 1 psi. Okay, the asterisks are the similar to previous. So again, what comes out of the turbine is right here. Okay, then what comes out of the condenser we had before as well, where I have 1 psi and saturated liquid. Again, that's basically state 3 over here, what comes out of the condenser. Okay, so again, what's different are these 100 psi and then state 7, what goes into the boiler. Okay, now going from state 1 to state 2, this is a isentropic process. So the entropy stays the same through the process. Okay, going from 1600 to 100 to 1 psi. Okay, so I know that the entropy is the same. I know the pressure is at 100, so I can look up H2 just simply going to 100 psi and 1.63. That gives me an H of 1210.7 when I do the interpolation here. Okay, so 1210.7. Okay, now going over here to state 5 is the next H I need. Again, this is on the back side of the pump. Okay, so you'll remember on a pump, the it's a incompressible steady state reversible flow, right? So that means V4 times P5 minus P4 equals H5 minus H4. So the work of the pump is not only the change in enthalpy, but it's V change in P as well. And I know V, I know both P's, I know the enthalpy 4. The only thing I don't know is the enthalpy at 5. I can calculate that and get 70.07 for the enthalpy at 5. That's what gets plugged into the feed water heater along with state 2. These are both at 200 psi. What comes out of the feed water heater, again, it says saturated liquid exits the feed water heater. So here I'm going to look up H6, and then knowing that it gets thrown into a pump just like here, I'm going to look up V6 as well. So now I'm at saturation. I go to 100 psi. Okay, and I'm a saturated liquid. So saturated liquid, my enthalpy is 298.6, and my volume is 0.01774. So I'm going to take those values and plug them in here. So I get 298.6 for the enthalpy, and then the volume is 0.01774. Now, this gets thrown in the pump up to 1600 psi, so I'm going to use the exact same idea here, where V6 times the change in pressure equals the change in enthalpy. And again, I know everything here. I know all my 6 values, so V6, P6, H6. I know P7 is 1600. The only thing I don't know is H7, and I can calculate that to be 303.5. Now I have set my states. Okay, all of my states are set. So the next thing I need to do is figure out what's going on with that mass flow, right? Find the percentage that is pulled off at state 2. Okay, and the equation for that, again, just using, the fact that 2 and 5 are coming in, one's at y, one's at 1 minus y as a percentage. Okay, and then what goes out is all of it after they mix. So that means y, using the equation, is H6 minus H5 divided by H2 minus H5. And from that I can find that the percent of the mass flow that's pulled off at state 2 is actually about 20%. It's 0.2004. meaning 80% of that mass flow continues on at state 3 into the condenser, and then 20%, 80% come in here, and then 100% comes out as far as the mass flow goes. I need that because, again, the turbine, 100% of it goes through here, 80% of it goes through here. Then I actually have two pumps. 80% is going through this pump, and 100% is going through this pump. So when I find the work of the cycle, like I'm looking for here, I'm going to take my mass flow, right? And I'm going to multiply that times, well, 100% of the mass flow going from H1 to H2. That's the work of the first turbine, plus 80%, because again 20 gets pulled off here, 80% goes through the rest. So that's going to be 1 minus y times H2 minus H3. So that's the work of each of the turbines. Then I have to subtract off the pumps. The first pump only has 80% going through it, and that's going to be H5 minus H4. So I take 80% times that change in enthalpy. And then 100% goes through this pump, but I'm subtracting that off too. That is going to be H7 minus H6. So again, the mass flow times 100% through this, 80% through this, those two added together, and then I subtract off 80% of this pump and 100% of that pump. I know all these H values. I can find the work of the cycle then to be 8 times 10 to the 8th BTUs per hour. Comparing that to my initial one, where I get actually 8.84. Okay, so I have a little bit less. Again, that's because I'm pulling off not all of the mass flow is going through the turbine, so I don't get as much output as I did before. However, my Qin is going to be smaller now, so hopefully my efficiency will improve, which is going to be the work of the cycle over my Qin is right here, where I'm going from state 7 to state 1, where state 7 is a little warmer than it was going into the previous boiler. So that's going to be all of the mass flow times H1 minus H7. And that gives me an efficiency of 45.9%. And you can see compared to previous one at 42.9%, I actually do have an increase in efficiency. So even though I don't get as much work out, the fact that my boiler's not working as hard actually improves the performance of the total system.